Okay, so we are ready to review for the second of our three exams. This is going to cover chapters 39, 40, and 41 in the textbook. So we're moving along in modern physics, and the first one starts with the quantum mechanics of atoms. So, and we're going to focus on one electron atoms because the solutions are easier. The equation is easier to solve, but we'll see that there are some things that apply generally. And so we start with the Schrodinger wave equation for hydrogen. And so we have the differential equation for the wave function as a function of position. And then we have the potential energy, which is the electrical potential energy between the nucleus and the electron. And it's only one electron, which makes this quite a bit simpler than it otherwise would be. And then that's equal to the total energy multiplied by the wave function. So this is the time independent version of the equation. So solving this equation requires three integer variables. The first is n, the principal quantum number, which is basically the same n that Bohr found. And but there are additional quantum numbers that you need, and you don't really notice them until the atom is exposed to a magnetic field. But you have the orbital quantum number, which is related to the angular momentum of the electron. So angular momentum, capital L, is quantized. It's equal to the script of, or rather the square root of script L times script L plus 1. So that's square root multiplied by h bar, which is the Planck's constant divided by 2 pi. And then we have the orbital magnetic quantum number. And, that's related to the z component of the angular momentum. So, the direction of the magnetic field matters. And so that's equal to the orbital magnetic quantum number, again, multiplied by h bar. And you find these different energy states by exposing the atom to a magnetic field. So in quantum mechanics, n can be any positive integer. Script L can be any integer between 0 and n minus 1. M sub L can be any integer between negative L and positive L. So there's a limit to how many quantum numbers you can have for a particular value of n. All possible states within the same value of n are said to form a shell. All possible states with the same values of n and script L are said to form a subshell. Quantum mechanics allows for orbits along a sphere rather than a circle as in the Bohr model. So it's not like planetary motion, which is what Bohr initially thought. The electron can be any place really along a sphere, and even that is crude. As as we go on, you'll see that r can vary, and it's more like a probability of where r is rather than meaning the orbital radius than being at a specific value. So the fourth quantum number comes from electron spin, and this is a relativistic effect. And so Dirac came up with the version of the Schrodinger equation that takes relativity into account. And so it's quite a bit more complicated than the Schrodinger equations we introduced here. And so basically you have what's called fine structure, tiny splitting of energy levels that comes from what's called the spin magnetic quantum number, which can be either plus 1/2 or minus 1/2. And again, you don't see the difference unless the object is moving at relativistic speeds and is exposed to a magnetic field. So according to the Pauli exclusion principle, no two electrons in the same atom can have the same values for all four quantum numbers. And so it's the ground states um, when every electron is, or when all the lowest possible states of the electrons are occupied. And, that's what helps to define the periodic table and the various properties associated with the periodic table. So spin angular momentum, or capital S, is the square root of S times S plus 1 times, again, H bar. So that's equal to radical 3 over 2 times H bar. So that doesn't change. And the Z component of spin is either plus 1/2 H bar or minus 1/2 H bar. So again, that's H over 4 pi or negative H over 4 pi. So the wave function has a number of allowable solutions. For the ground state of hydrogen, we can talk a little bit about that solution. It's 1 over the square root of pi r naught cubed, where r naught is the Bohr radius, 0.0529 nanometers, that we talked about in the previous chapter, and then multiplied by e to the negative r divided by r naught. And so again, R naught is equal to H squared times epsilon naught. Epsilon naught is the permittivity of free space. So that's 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And you're dividing that by pi times the mass of the electron times E squared, where E is 1.602 times 10 to the negative 19 coulombs. And the ground state is normalized so that when you integrate over the wave function over all space, you get a probability equal to exactly 1. So you're integrating over a volume. And the volume is, or the differential element of volume is 4 pi r squared dr. So you can have the 4 pi because there's no angular dependence for the potential energy. And so it only depends on r. And so that's where the 4 pi comes in. And so the radial probability distribution is 4 pi r squared times the square root of the wave function, which you can write as 4r squared over r naught cubed times e to the negative 2r over r naught. And again, you integrate that from r equals 0 to r equals infinity, you will get exactly 1. The most probable radius, or the radius with the highest probability of being the electron's location, is determined by setting the derivative of this function equal to 0. And when you do that, you get r naught, the Bohr radius. And if you want to find the probability that an electron is located between points A and B, you integrate the probability function between A and B. Now with quantum mechanics, you have 4 subshells, the S, P, D, and F subshell. Those are the 4 lowest subshells. And those take up the ground state of nearly all the atoms in the periodic table. So if you're only looking at the ground state, you don't have to go beyond the F subshell. But the S subshell corresponds to L equals 0, and so there are 2 possible states in that subshell, and that's any L subshell. So it could be, or any S subshell. So it could be 1s, 2s, 3s, and so on. The P subshell corresponds to L equals 1. There are 6 states. The D subshell corresponds to L equals 2, and there are 10 states. And the F subshell corresponds to L equals 3, where there are 14 states. And so you build up from there. So the ground state has hydrogen has 1 electron in the 1s state. For helium, there are 2 electrons in the 1s state. Again, you have ms is equal to plus 1/2 and ms equals to minus 1/2. For lithium, you need to go to n equals 2. So you have an additional electron in the 2s state. For beryllium, there are 2 electrons in the 2s state. For boron, you now have an open electron in the 2p state. And then you keep working your way up. And so you see how it looks. And after 10, you've completed the n equals 2 shell. And then you start with the n equals 3 shell. The n equals 3, you'll notice that you go to 4s1 and 4s2 before you go to 3d as you're moving up. And so then you have the periodic table with a bunch of different common properties. So uh, column 1 are the alkali metals. They have one extra electron in an s state. The column 17 are what are called the halogens. They're one electron away from a complete p subshell. So column 1 and column 17 react with each other readily, and those are called ionic bonds. And then you have what are called the noble gases in column 18. They have complete S and P subshells. They do not react very often with other elements. And so then you have the transition metals, which are the D subshells, and then, or rather, these are the transition metals. Then you have the lanthanoids and actinoids, which are the F subshells. And then you have what are called poor metals. Those are where you find semiconductors like silicon, for example. And these don't conduct electricity as well. And then you have the other nonmetals. And so you have the gases, and then you have things like I said, silicon is a semiconductor. So, and gallium is as well. And carbon is technically considered a semiconductor. So elements with similar properties are placed in the same column. And again, we talked about the noble gases and the alkali metals, the transition elements, the actinides and lanthanides. Now, the atoms, or the number of atoms in a given element, were determined from what are called characteristic X-ray spectra. And so for elements with high Z, a transition to the n equals 1 state results in a high energy X-ray photon being emitted. And so if a beam of electrons is fired into a metal, the collision will produce X-rays. And there'll be a spectrum of X-rays that shift as the voltage is varied. So, the more energy you give to the electron, the more energy you can, the outgoing X-rays will have. But there are also two distinct lines called characteristic X-rays that depend on the substance used. So there are specific wavelengths that are unique to each element, where you have this spike in X-ray intensity. And so the shorter X-ray, so K alpha, is inversely proportional to Z squared, unless the transition is from n equals 2 to n equals 1. And so in that case, it's proportional to Z minus 1 squared. But, so there's a pattern in the wavelength. And so you can use that to determine the atomic number of given elements, especially of the metals. And another way you can, another type of X-ray that you can see is what's called Bremsstrahlung, when an electron is slowed down. So you expose the electron to a stopping potential, and as it loses energy, it gives off a photon. And so the shortest wavelength in the X-ray spectrum occurs when the electron gives up all of its kinetic energy. And so, when it hits something, it loses all its kinetic energy. And so that's the edge of that's the lambda naught here. But again, you have two special wavelengths. The rest of it depends on the energy of the energy of the electrons, which is supplied by the potential difference. So then we talk about how you find the other substates. So you have the Bohr model, And you can write the magnetic dipole moment in terms of the angular momentum, capital L, or in terms of the square root of script L, L plus 1, so the quantum number. So the magnetic dipole moment becomes E times h bar over 2n times the square root of L times L plus 1. And this alters the potential energy of the electron if it's exposed to the magnetic field. So we define the z-axis as the direction of the magnetic field. You get the potential energy is equal to the Bohr magneton times the magnetic quantum number, and so m sub L times the z component of the magnetic field. So you expose the electron to a magnetic field, you see different potential energies. So the quantity mu sub b is known as the Bohr magneton. It's equal to 9.27 times 10 to the negative 24 joules per Tesla. And the Zeeman effect, it was first postulated as an example of theory leading an experiment. So Zeeman figured out that an atom placed in a magnetic field would have its energy split into levels. And you can tell what those levels are based on the Bohr magneton. And the Stern-Gerlach experiment verified the Zeeman effect. And if it's the spin angular momentum that's affected rather than the suborbital angular momentum, then delta U is equal to 2 times the Bohr magneton times B. So that brings us to the total angular momentum. So vector J is equal to vector L plus vector S. So orbital angular momentum plus spin angular momentum. And so we write, and that's also quantized, that J is equal to the square root of J times J plus 1 multiplied by H bar. J can be either L plus a half or L minus a half, with the exception being that J is always greater than 0. So if L is equal to 0, J can only be equal to 1/2. And so we talked about some properties that are tied to quantum mechanics. And so fluorescence occurs when an electron is excited by a UV photon and then emits visible photons as it returns to its initial state. So again, sometimes you can expose a substance to UV light and it will start to glow. And that's what fluorescence is. And again, there's a quantum mechanical explanation for it. And then the next thing is phosphorescence. That's when electrons reach a stable excited state and then gradually emit photons as they return to their initial state. So maybe you have a watch like this one that glows in the dark if you turn the light off. And so what happens is it's exposed to the light, the electrons absorb that photon and they reach an excited state. And they stay in that state for a long time. And so they gradually emit the photons over time. And so if you turn the lights off, a phosphorescent material will glow for a while. And, due to the energy that it's previously absorbed. And the last thing we're going to talk about in this chapter is lasers. And lasers work on the principle of stimulated emission. So a photon of a specific wavelength, if the rules of quantum mechanics allow, can cause an excited electron to emit a photon of the same frequency that is exactly in phase with the incident photon. And Willa is right here. Inga, I'm in the middle of... Can you please close the door? So in a laser, many electrons are excited, and one photon of the right frequency can trigger the release of many identical photons. And when they're in phase with each other, that's called being coherent. So a laser emits coherent light of a specific wavelength, and all the light is in phase with each other. That makes it very convenient for doing optical experiments because it's easy to determine the interference pattern from a laser light. So the requirements for a laser cavity are an inverted population where more atoms are in an excited state than in the ground state. And so the excited state has to be what's called metastable, which means it doesn't decay immediately. It remains in the excited state for a prolonged period of time, unless you have stimulated emission, which we just talked about. So unless it's stimulated by incident photons. So there are two types of lasers: a pulsed laser, where the energy input or output is periodic, meaning instead of a continuous beam, it shoots out a very intense beam over a very short period of time and then does it again and again and again at a certain frequency. Whereas a continuous laser, uh, typically smaller power, at least over the, at least, um, per instant of time, is smaller power, but it's continuous. So it might have more total energy than a pulsed laser, but less power over the time that the laser is active. So that was chapter 39. And so we now move on to chapter 40, which is molecules and solids. So we go from atoms to molecules. So now we're going to talk a little bit about the bonds. And if you've taken a chemistry class, you probably know the basics of this already. But we're going to look at things from a quantum mechanical point of view. So a chemical bond is when atoms join together so as to function as a single unit. There are two basic types of chemical bonds. There is a covalent bond where electrons are shared. So you think H2 or H2O, for example, O2 or O3, N2, molecular nitrogen. These are examples of covalent bonds: carbon dioxide, CO2, methane, CH4. These are examples of covalent bonds that the electrons are shared between two atoms and orbit both nuclei. And so those electrons work in pairs. And the electrons must have opposite values of, the electron pairs of opposite values of m sub s. And so the two electrons lose energy, making the molecule more stable and requiring a bond energy to break the atoms apart. The other type of bond is the ionic bond, where one atom with extra electrons outside a closed S or P shell gives an electron or maybe several electrons to another atom that needs them to complete a shell. So the most obvious example of an ionic bond is sodium chloride or table salt. So the extra electron in sodium feels more attracted to the chlorine atom than to its own sodium atom. But once the electron moves over to the chlorine atom, you now have a positive a positive sodium ion and a negative chlorine ion. It's gained an extra electron. And so they're immediately attracted to each other. And so you have crystal structures that result. So we're going to go over now the basics of potential energy in the atom. So we're starting with 2 point charges. So a proton and an electron. And so if they attract, the attractive force, so the potential energy increases as the electron approaches the proton. If you have two protons or two electrons, the potential energy increases as you get as they get closer to each other. So again, for like charges, the potential energy is positive. For unlike charges, the potential energy is negative. For molecules where there are combinations of protons and electrons, it's a bit more complicated. So a long distance away, when the nuclei are a long distance away from each other, the electrons are in between, and there are electrons in between them, and that causes attraction. So you have a negative potential energy. And then as they get closer, that potential energy increases. So you have the electrons between them. But then as the nuclei get closer to each other, it's less likely to have electrons between them. And if they're on opposite sides, then the potential energy becomes positive. So the closer the nuclei get to each other, once you pass a certain minimum, then the potential energy starts to increase and eventually becomes positive. Um, and because once you reach a potential energy of 0 and you get to a positive potential energy, that means the electrons are more likely than not to be on opposite sides of the nuclei rather than between them. And that, again, that causes repulsion rather than attraction. But you have the minimum potential energy, and that's called the binding energy. That's the ideal location. That's the stable equilibrium location. And um, just like in electricity and in regular dynamics, the molecules will tend to minimize tend to minimize the total potential energy, and work towards static equilibrium or stable equilibrium, excuse me. With more complicated molecules, so that's simply a hydrogen atom. For more complicated molecules, um, then you have a mixture of protons and electrons, and you actually have to overcome what's called the activation energy, which is sort of the highest possible positive energy. So you need to give the two nuclei a velocity relative to each other in order to, or enough kinetic energy um, so that they can get close enough to bind. And that's basically what this means. You have to overcome this potential energy before you can bind the molecule. So you have an activation energy and a binding energy. Um, uh, so when you have a large number of electrons, yeah, you have some electrons between them, but then you have electrons on opposite sides as well. And so you initially have more force pulling the nuclei away from each other. And so again, you need to overcome that activation energy to get the nuclei close enough to each other that they can bind. But you also have a binding energy, the stable minimum potential energy. That's the most stable configuration. And then you have, we talk about weak or van der Waals bonds. So strong bonds occur within molecules. Weak bonds occur between molecules due to electrostatic attraction. So with ionic um, bonds, the electrostatic attraction is pretty obvious. And so any sort of dipole-dipole bond would qualify. A hydrogen bond is when one of the binding atoms is hydrogen. And so these are the strongest of the weak bonds because it's easy to get close to a hydrogen nucleus. And that's an essential part of protein synthesis. So we're bringing biology as well as chemistry into this. And you can see that a lot of that has to do with quantum mechanics. So with molecules, additional energy levels become possible because the molecule can rotate around its center of mass. So the nucleus will have spin, and the atoms of the molecule can vibrate relative to each other. So, the molecule can have spin, the different nuclei can spin around each other, and the different nuclei can vibrate relative to each other. So that produces different energy states, and molecules have much more complicated spectra than atoms do. They don't typically absorb in specific lines, they absorb in what are called bands. So these correspond to one vibrational or rotational state. And so they appear as very closely spaced lines. With low resolution, they appear as continuous bands. So what are the rotational energy levels? So again, these are the nuclei rotating around each other. So the rotational kinetic energy, this is going back to physics 1, is equal to 1/2 I omega squared, where I is the moment of inertia and omega is the rotational velocity. And so you can write, remember the angular momentum is equal to I times omega. So you can write this as L squared over 2I. And we'll write it that way because L is quantized. And so we know what L squared is. And so we have, again, we have the angular momentum of the atoms in a molecule as they rotate is quantized just the way the angular momentum of an electron is quantized. So you have L times L plus 1 times h bar squared divided by 2I. So the selection rule, meaning jumping from one state to another, the selection rule only works in increments of 1. So the change in the energy state is equal to h bar squared over I times the higher of the L values. And so um, when you're emitting a photon, you're basically the photon will have an energy of h bar squared over I times the higher value of L. And the moment of inertia, where can be written as m1r1 squared plus m2r2 squared, but you can also write that in terms of the reduced mass. And so mu is the product of the two masses divided by the sum of the two masses, and then r squared is the distance between them. So you don't need to know the location of the center of mass, or you don't need to go through the trouble of determining that. You can figure out mu and you can figure out r squared, and that'll give you the moment of inertia. And so you can use those to figure out the rotational energy spectrum. As for vibrational energy spectrum, vibrational spectrum tend to be much more energetic, 10 to 100 times more energy than rotational levels, and with corresponding wavelengths in the tens of microns. And that's fairly important because that's typically the kind of energy that the Earth emits from its surface. Those are the kind of wavelengths that the Earth emits. And so when you have molecules in the air, that have a significant absorption band, you can, that energy can be, is kept in the air rather than being leaked out into space. And that helps to warm the planet. And so we'll talk a little bit more about that in a couple of minutes. But the vibrational frequency, F is equal to omega over 2 pi. So we can write that as 1 over 2 pi times the square root of k, where k is, you can think of that as an effective spring constant of the molecular bond, divided by mu, where mu again is the reduced mass. Energy states, vibrational energy states are also quantized. So you have an integer v plus 1/2, and then that's in parentheses multiplied by hf. And so the selection rule says that delta v is equal to plus or minus 1. So again, the energy state the energy states change in increments of 1. And so delta, so the energy level is equal to h times f. And so you can look at the vibrational bands and you can see them simply by looking at radiation from the Earth's surface that's traveled through the Earth's atmosphere. So if you have a low wave number, or inversely, you have wavelengths of 7 to 8 microns, you can see absorption bands due to water vapor and methane. Then you have an absorption band due to ozone between 9 and 10 microns. At 10 to 11 microns, there's very little absorption, and that corresponds to what's called the atmospheric window. So a lot of satellites have a channel at that radiation, or, at that wavelength, so you can observe radiation coming directly up from the Earth's surface. And, so that serves a very important function. Then at 15 microns, notice the sharp dip due to CO2, carbon dioxide. And that's why carbon dioxide is the most important of the greenhouse gases. That corresponds to the peak of the Planck black body spectrum, or close to the peak of the Planck black body spectrum, at least if it's measured in terms of watts per square meter per inverse centimeter. If you do it in watts per square meter per wavelength, the peak is actually shifted lower as far as wavelength goes. You would use Wind's law in that case. And to figure out the peak wavelength. And then you have, beyond the CO2 absorption band, you have another H2O absorption band. And so, those are the molecules in the atmosphere that absorb a lot of infrared radiation. Notice you don't see nitrogen and oxygen on this list. All the molecules you see have at least 3 atoms in it. Nitrogen and oxygen only have 2 atoms. They don't have the same kind of rotation that atoms with more, or molecules with more than 2 atoms would have. And as a result, they're not sensitive to the kind of radiation that the Earth emits. So they aren't nearly as sensitive to the kind of radiation that the Earth emits. And now we're going to talk more about bonding. Some substances form what are called crystals. And so in a crystal, the atoms, the ions, and the molecules line up in an orderly fashion. And so the crystalline structure is called a lattice. One type of crystal is a metal. In metallic bonds, electrons are only very loosely bound to the parent nucleus. So you sort of have an electron cloud holding the different nuclei together. But the electrons are basically free to move. They don't stay in one particular location. They are free to move. And so again, we're going to the basic example of an ionic bond, sodium chloride. So you have a face-centered cubic lattice structure. And a given ion is surrounded by ions of opposite sign. And so the potential energy is negative, and it's given by this relationship, negative alpha, where that's a proportionality constant, times 1/4 pi epsilon naught, times E squared over R naught, where R naught is the equilibrium distance, basically the distance at which you have the binding energy. And then multiplied by, in parentheses, 1 minus 1/m, where m is an integer. So alpha depends on the atom, or on the molecule rather, and m depends on the molecule. So for sodium chloride, alpha is called the Madelung constant, is 1.75, but that's substance specific. And the variable m is also, and that's an integer, and that's also substance specific. A conductor can be treated as a potential well, where its edges have functionally infinite potential energy at room temperature. So basically, you don't see too many electrons jumping off the metal. But so the potential energy is much higher, and that's due to the the fact that air is a very large insulator. It's very hard for electrons to get to penetrate through the air. You need a really powerful electric field for that to happen. So the size of the well is very large by atomic standards. So as a result, the allowable energy states are very, very tightly packed. Again, you can think of an infinite square well with a very large value of L. And instead of a rather broad spacing, the spacing is actually kind of tightly packed. And you can talk about the density of the states, the number of allowable states per unit volume. And that's a function of the energy. So The greater the energy, the more allowable states per unit volume that you have. And so the number of electrons per unit volume, you go from 0 to the Fermi energy, which is the maximum occupied energy state at 0 kelvins. So at absolute zero. So basically, it's the ground state. And you basically the highest state that has an occupied electron when all the electrons are in the lowest possible energy state that they have. And so you can determine this for different elements or different substances. And so you have a complicated function of the Fermi energy. And so it's equal to h squared divided by 8m times 3 capital pi, or 3n over pi v, where again n over v is the number of electrons per volume, times, and that's to the 2/3 power. And so, I mean, you can figure out the Fermi energy for different elements. And then you have the probability that a given energy state will be occupied. And so you see the equation F sub E is equal to 1 over E to the E minus EF divided by KT plus 1. And so what you get from that is that the low energy states are nearly always occupied. And then you pass the Fermi state, and what's above it is very rarely occupied. The energy states above the Fermi energy are very rarely occupied. In a if the temperature was 0, then you would have a solid line, a perfectly straight line downward. So you would have full or 1 down 0. But you, as the experiment or the computer programming assignment that you did showed, that as the temperature increases, that you start to have the probability of these states slightly below the Fermi energy starts to decrease, and then the probability of the energy states slightly above the Fermi energy starts to increase as you increase the temperature, and it becomes more pronounced as you go on. And so then we move on to what's called the band theory, and this works. This is how we explain the difference between conductors and semiconductors and non-conductors or insulators. So when 2 hydrogen atoms combine to make a molecule, the energy states split into 2 levels. When you have a lot of different atoms in one metal, for example, the energy states split into very many, very closely packed levels, and they form an essentially continuous band. And in conductors, the highest energy band is only partially filled, which means electrons can travel through them fairly easily. With insulators, the highest band containing electrons is completely filled, and the energy gap, or the difference in the energy level between the filled or the valence band and the next highest band, which is called the conduction band, is too high for the electrons to jump. So getting back to physics 2, you need a strong electric field to get the electrons to cross through the air. So the electrons need to have a lot of energy before they can get to that next band. Or you need to have a lot of energy in order for the electrons to, present for the electrons to get to that next band, or to get them to jump and to make conduction possible. And in semiconductors, the energy gap is not so high, meaning that it's not that hard for the electrons to get enough energy to jump to the next level and pass through. And sometimes you can affect the conducting ability of semiconductors by adding impurities to the crystal structure. So this is called doping. And so if you dope silicon with arsenic, you put extra electrons above a complete shell and enhance conductivity. And that's called an N-type semiconductor. If you dope the silicon with gallium, you have holes in the complete shell. And so if there are electrons available, they might move into that shell. And so or they may jump from one point, from one hole to another hole, and or from one state to another state. So the whole, you can think of it as the hole moving rather than the electron moving. And so that affects the behavior of the structure. And so you can have what are called diodes when you put an N-type semiconductor next to a P-type semiconductor. So here, when you have the diode facing one way or in the positive direction or in the forward direction, the electrons get to the N-type and they can pass through that very easily and then get to the positive type and get through. Whereas if you work in the other direction, what happens is the electrons come in and fill the holes and they don't get to, they don't make it to the band. So, or rather to the N-type semiconductor then. And so one way allows movement, one way doesn't allow movement. And so you can still get flow if the voltage exceeds a breakdown point. So if you reach a maximum voltage, or you reach a minimum voltage that you're exposing the electrons to, they'll be energetic enough to cross into the N-type portion of the semiconductor or of the diode, and then get you'll have current flowing. So there's a threshold voltage. In what's called a Zener diode, the constant voltage and steady current past the breakout point are allowed by design. Rectifiers are diodes that turn an AC input into a DC output. So I don't know if you did that lab experiment in 232, rectifiers are used in DC power supplies. You get AC out from the plug, but you use a rectifier to make it a DC output. So basically, you're using diodes to make the output DC. In a light emitting diode, electrons settle into holes and emit photons. And so, they settle into the hole and they emit energy to, they emit light, basically, is what they're designed to do. They emit energy corresponding to the band gap. So they come in and they settle into the hole and they emit light. And then we have transistors, and transistors are a very important part of computing technology. The smaller you can make this transistor, the more energy you can store. But it basically has a p crystal sandwiched between two N's or an N crystal sandwiched between two P's. And they're very useful for amplifiers. And so that was chapter 40, and that brings us to chapter 41, which is nuclear physics and radioactivity. So now we're going inside the nucleus. So the atomic nucleus consists of protons and neutrons. Neutrons have a slightly higher mass than the proton. As you can see, there's not a whole lot of difference. We define Z as the atomic number, which is the total number of protons. And so all atoms of a given element have the same value of Z, but the number of neutrons, or N, can vary. So you have different isotopes for the same element. And so we define A as the mass number, which is the total number of nucleons, or protons and neutrons, in the nucleus. So A is equal to Z plus N. So an isotope is typically denoted in the following form. You have A, the total number of neutrons, Z, the total number of protons, and then X is the chemical symbol. The chemical symbol sort of implies the number of protons, so sometimes the Z is ignored. So sometimes you won't see the Z with this. So the atomic nucleus can be, the size of it can be approximated from the equation R is equal to 1.2 times 10 to the negative 15 meters. So that's basically the size of a proton, multiplied by A to the 1/3 power. Now, the mass in kilograms are an inconvenient mass unit to work with at the atomic and nuclear scale. So what are typically used are unified atomic mass units. They're normalized so that a carbon-12 atom has a precise value of exactly 12 U. And so from that, we get a value of U is equal to 1.6605 times 10 to the negative 27 kilograms. So the proton and the neutron have slightly more than one atomic mass unit. One atomic mass unit corresponds to an energy of 931.51 mega electron volts over C squared. So basically, you take the rest energy, you multiply it by C squared, and then convert it to mega electron volts, which is 1.602 times 10 to the negative 13 rather than 10 to the negative 19. Or rather, you multiply by C squared to get the energy in joules. And then you multiply by, like I said, 1.602 times 10 to the negative 19, or 10 to the negative 13, to get the energy in mega electron volts. So the energy levels in the atomic nucleus are also quantized. So you have a nuclear spin quantum number I that can be an integer or a half integer, and the total nuclear angular momentum is the square root of I times I plus 1 over h bar, or multiplied rather by h bar. And so we define the nuclear magneton as mu n times eh bar over 2 times the mass of the proton. So it's related to the Bohr magneton, or it's similar to the Bohr magneton, at least in terms of structure. But mu, the magnetic dipole moment of a proton, is given by this. So it's not an integer multiple of the nuclear magneton. And for a neutron, it spins in the opposite direction that the proton does. And its magneton is a little bit less. So the total mass of a stable nucleus is always less than the sum of its protons and neutrons. So where nuclear physics is concerned, the whole is less than the sum of its parts. So there's less mass, which means there's less energy. And so that difference in energy is called the binding energy. So it's the difference between the mass of the sum of the parts and the mass of the whole. And it's the basis of nuclear fission and fusion, which we'll talk about, I believe, in the next chapter. And so the strong nuclear force is the attractive force that keeps the protons packed together within the nucleus. So remember, the protons will repel each other if left to their own, if the only force was the electrical force. But the strong nuclear force has to keep the electrical force balanced out so the protons remain in place. However, sometimes the protons don't remain in place, and sometimes other things happen as well. And so you have what's called radioactivity, when atoms emit either radiation or particles without any prior stimulation. And that comes from the decay of an unstable nucleus. So something happens inside the nucleus. And there are quantum mechanical explanations, certainly for an alpha decay, and also for a gamma decay as well. For beta decay, we'll have to go into uh, quantum chromodynamics, I believe it's called. But we'll talk about particle physics to explain beta decay. But the nucleon number is conserved in each process. So the total number of protons and neutrons is conserved. In beta decay, the number of protons and neutrons is changed, but the sum remains conserved. So in alpha decay, uranium decays into thorium, 2 steps below it in the periodic table, and helium, an alpha particle. So you have a helium nucleus with 2 protons and 2 neutrons. Radium decays into radon and helium. So that's another example of an alpha decay. In both cases, mass number and electric charge are conserved. The total, A is conserved and Z is conserved. So when the daughter nucleus is different from the parent nucleus, you have what's called transmutation. So you have the parent nucleus with an atomic number of, or with a mass number of A and an atomic number of Z. The daughter nucleus, A will be reduced by 4 and Z will be reduced by 2. And those lost protons and neutrons are a helium nucleus that gets emitted from the parent nucleus. So the mass of the alpha particle is given in mass units by this. And again, don't forget the conversion, 931.51 mega electron volts per c squared. So typically when we want mass, it's easier to work with U than with kilograms if you're on the nuclear scale. And with energy, it's easier to work with mega electron volts than joules. So the mass of the parent nucleus is greater than the mass of the daughter nucleus plus the mass of the alpha particle. And the remaining energy gets converted into kinetic energy. So the alpha particle and the parent nucleus will recoil from each other. Momentum is conserved. So whatever momentum the alpha particle has, the daughter nucleus will have in the opposite direction, the same magnitude momentum in the opposite direction. However, typically, the alpha particle is quite a bit less massive than the daughter nucleus, so most of the kinetic energy goes to the alpha particle. And so how do you explain this using quantum mechanics? Well, you can think of, a square well potential, and due to the strong nuclear force inside the nucleus and a Coulomb potential immediately outside the nucleus. And so you can think of it sort of as, so you have the square well, but then you have the decreasing potential outside the nucleus. So you can think of it as barrier penetration. Every so often, a proton-neutron pair gets enough energy to escape. And that's what alpha radiation is. And okay. So that brings us on to beta decay. And in beta decay, you have a neutron decay into a proton plus an electron. So the mass number, or the total mass number, remains the same, but now you've turned a proton to an electron, or turned a neutron to a proton. And so what happens is the atomic number goes up. So A is constant, A is conserved, but Z goes up. And so an electron is booted out of the nucleus. And but you may have some additional energy. And what here's an example of scientists or of experiment leading theory that energy and momentum conservation required the presence of an additional particle, not just the electron. So typically in beta decay, you have a neutrino in addition to the electron. And a neutrino has very, very little mass. It's still yet to be determined. It's known to be less than 2.5 times 10 to the negative 37 kilograms. But physicists are very confident the number is not zero at this point. So the neutrino is zero charge, a spin of half h bar. And like I said, it's the maximum possible value that it could have is 2.5 times 10 to the negative 37 kilograms. We know it has to be, at least, it can't be any more than that. It could be less than that. But again, physicists are fairly confident the number is not zero, like a photon, for example. Positrons can be emitted, meaning an anti-electron. So you have a positive charge. If the beta decay occurs in an isotope with relatively few neutrons per proton. And so how do you determine that? Well, this is the line that goes above the n equals z line. That's where the stable nuclei are. And so basically, for an atomic number of 0 to 20, stable nuclei typically have as many protons as neutrons. But as you go above 20, the number of neutrons in a stable nucleus, or the neutrons, tend to outnumber the protons in a stable nucleus. And so that ratio starts to get bigger, gets steadily bigger, the more, the greater the atomic number involved. And what's in beta decay, if your neutron number, or if n is below the number for a stable nuclei, then when beta decay occurs, you're more likely to get a positron and an antiproton than a regular, so you're more likely to get antimatter than matter out of that. And then the last one is gamma decay. So a nucleus can be in an excited state, but the energy levels are much more spread apart inside the nucleus than they are for an electron. And so when an excited nucleus goes from a high state to a low state, it emits much more energetic photons. And so this is called gamma decay. And so you have an excited nucleus emitting a gamma ray, so a very high energy photon. And that brings us to the notion of half-life and decay rate. So half-life is the amount of time it takes for half of a radioactive material to decay. And so we'll talk a little bit more about that in a minute or two. But now let's talk about decay rate. So the number of decays, dn, over a time dt, is proportional to both dt and n itself. So you double the number of radioactive nuclei in a sample, you'll double the decay rate. And or you'll double the decay rate. And so dn, the number of decays, or the differential number of decays, is equal to negative lambda, a substance-specific constant that's called the decay constant, times n times dt. Or the derivative of n with respect to time is equal to negative lambda over n. And so the activity is R is equal to lambda over n. And so that's how much activity you're getting at a given instant. So from this, you get the radioactive decay law. You basically do some integration, and that n is equal to n naught, which is the number of radioactive nuclei at t equals 0, So n naught times e to the negative lambda t. And then a half-life is the amount of time it takes for the radioactive sample to decay. So that's just equal to lambda, or the natural log of 2 divided by the decay constant. And the mean life is the average lifetime of a radioactive sample, which is just the inverse of the decay constant. And that's equal to the half-life divided by the natural log of 2. And so you have what's called a decay chain, when radioactive isotopes can decay into other radioactive isotopes and so on and so on. So it's typically a combination of alpha and beta decays. And unstable isotopes with relatively short lifetimes will have their supplies readily replenished. But some isotopes have very long lifetimes. So you look at uranium, for example. Uranium has a lifetime of 4.5 billion years, or 4.5 times 10 to the negative 9 years. So the first step takes a long time. But then you have beta decay, and then you have a series of alpha decays. Eventually, uranium 238 will decay to lead 82. But there's a series of alpha decays, which are the red lines, and beta decays, which are the horizontal green lines. And you can see that there are multiple paths that can be taken, but the eventual end product is lead 82. Or rather is lead, excuse me, not 82, 206. So this is the mass number, and this is the atomic number. But radioactivity is useful for determining the age of certain objects. And so the two most common types of objects used for dating are carbon-14, or the two most common substances are carbon-14 and uranium-238. Carbon-14 has a half-life of 5,730 years. That makes it very useful for dating organic material corresponding to human pertinent to human civilization. So it can date organisms between 1,000 and 60,000 years old. And the reason is that a living organism is readily exchanging carbon with the surrounding air. So living organisms have the same ratio of C12 to C14 as the Earth basically does. But when the organisms die, they're no longer exchanging carbon with the Earth. And as a result, the carbon-14 will eventually decay, but it's not being replenished. And so you can use the ratio of C12 to C14 to figure out the age of the organism. And uranium-238, with a half-life of 4.9 times 10 to the 9, or 4.9 billion years, is very useful for determining the age of rock. So let's say instead of a few thousand years, you want a few million years and beyond that, you use uranium to do that. And radiation can be detected a couple of different ways. The first detector used to detect radiation was called the Geiger counter. It could detect the emission of charged particles, so beta particles, for example. The scintillation counter, so if a particle comes in, the scintillator enters an excited state and then emits visible light as it's going down. So basically, a scintillator glows in the presence of radiation. A photomultiplier tube converts incident radiation to an electric signal. You can use that to measure the intensity of lasers, but you can also use it to measure the intensity of radioactivity or radioactive substance, or the decay rate. More high-tech devices use more high-tech detectors. So you have a silicon wafer semiconductor where a particle etches a track onto the surface. A photographic emulsion, ionized atoms leave a mark. In a cloud chamber, gas molecules condense on ionized particles when they travel through it. So you not only detect the presence of a particle, you can figure out its track from that, or its trajectory. And the same is true from a bubble chamber. So you have a superheated liquid, and when a radioactive object goes through, it evaporates the superheated liquid it comes in contact with. And again, that gives you a track. And you can also use what's called a wire drift chamber, where you have high voltage wires. And when ions interact with the high voltage wires, they send a signal that a computer can use to determine the track. So again, we're getting, it's the most high tech example. So we have means not only of figuring out the presence of radiation, but also the trajectory of the radioactive particles. And if you've got time, high speed photography, you could possibly figure out the momentum and kinetic energy, the velocity, the momentum, and the kinetic energy of the particles as well. And so you can figure out a lot of information that way. So those were the 3 chapters on the exam. So if you have any questions before the exam, you can email me. I'm thinking for Friday, we'll do the exam remotely, maybe from 8:30 to 10:30. And then I think we're meeting at 12:30 for an experiment. So if you don't have any further questions, why am I even saying that? So if you have any further questions, you can email me. If you don't have any further questions, you can see me on, I'll see you on Friday.